Hello and welcome to the Rackspace Fanatical Support for AWS webinar, AWS Best Practices Designing Scalable Architectures. Good morning or good afternoon, depending on where you're joining us from. My name is James Cow. I'm the Director of AWS Strategy and Architecture at Rackspace, and I'm joined today by Jerry Hargrove, one of our Senior Solutions Architects specializing in AWS. Just wanted to thank everyone for joining us today and taking the time out of your busy days to spend an hour or so with us talking about these best practices. We're all aware that AWS provides many services and products that are designed to help us take advantage of the benefits of running scalable workloads in the cloud, but really knowing how to utilize these services to build both full tolerant, highly available, and most importantly, cost-effective applications and workload architectures is something that often requires a lot of expertise or experience in using those products and services. And it can be quite hard to find that expertise. So during this webinar, myself and Jerry are going to tap into over 15 years of combined AWS experience between us to outline some of the common design patterns or best practices that you would typically need to use when you start addressing architecture at a scalable and cost-efficient level on AWS. So at this point, I'm going to turn you over to Jerry Hargrove, who is going to introduce himself very briefly and then start the presentation for us. If you have any questions, please just drop them into the chat window during the presentation. We'll either try and answer them at the end of each kind of section, or maybe we'll take more Q&A at the end if there are a lot of questions. Jerry, over to you.
All right, thanks, James. I appreciate the introduction. Very quickly, as James mentioned, I'm a solutions architect with Rackspace. I focus on AWS. I've been working in AWS for about the last 7 years. What we're going to talk about today are some best practices around scalability and talking about some of the benefits of scalability in the cloud. If any of you have ever been to one of the AWS summits or reInvent, you've probably seen a slide, something a little bit like this, where Andy Jassy or one of his representatives gets up on stage and starts talking about some of the benefits of cloud computing. And it usually goes like this: you can replace your capital expenses with operating expenses and stop paying that money up front. You can, by moving to the cloud, you can lower your overall cost by leveraging some of the economies of scale that AWS provides you at their scale. You can stop guessing capacity. And this is what we're going to talk about today, and I'll come back to that shortly. You also, one of the benefits of moving to the cloud is just the agility and speed and innovation at which you can innovate. And you can move on the cloud. It allows you to move very quickly from one product to another, from one iteration to another, and allows you to focus on your product and the aspects of your product that differentiate yourself from your competitors, and not focus on the actual infrastructure that's underneath it. The final benefit is the ability to just go global in minutes. So once you move to AWS and you've got your application running in the Oregon region, you can literally be up and running globally in a matter of minutes, moving it to a region in Ireland or in Australia, wherever you'd like to be. It's that quick. So what we're going to talk about today is this third bullet item here, stop guessing capacity, and really how that relates to scalability. So I'm going to jump right into it and get started. What we're going to cover today are, at a very high level, some key concepts around scalability in the cloud and best practices around scalability. And we're not going to talk really much about horizontal scalability or vertical scalability, but some other concepts. We're also going to talk about cost and scalability. So what does the scalability cost you? Also, we're going to look at some aspects of developing for scalability in the cloud. And finally, operating at scale. So what are some of the best practices that you can adopt to operate in a truly highly scalable environment? And as James mentioned, depending on timing, we'll either take questions in between some of these sections, or we'll hold and we'll answer questions at the end. So I'm going to go ahead and get started. So the first thing we're going to talk about are some just high-level concepts around around scalability in the cloud. And one of the first things that we usually talk about is this idea of having the ability to only have the amount of capacity required to meet your current demand. Now, if you think historically about how this was done, typically what would happen is if you look at the upper right-hand graph here, your demand would fluctuate throughout the course of a year or some business cycle where you would have peaks and valleys. And what you had to do in the past, of course, is in order to accommodate your peak demand, you had to allocate enough capacity for that and have it in place 24/7 all year round. And so you ended up with this excess capacity. And actually that's sort of the story behind AWS and one of the incentives for them to start offering this service was that excess capacity that Amazon had. So if we look at the lower left-hand graph here, ideally what we would like to do, and this would be in the ideal world, would be to have our actual capacity meet our demand, such that we only ever had enough capacity on hand to meet our existing demand requirements. But often that's not a realistic goal, and there are a couple of reasons for that, where we still have to provision above the actual demand. You can see that in the right-hand, lower right-hand graph here. We usually establish some safety margin there, and we do that for a couple of reasons. Number one, there are fluctuations in actual demand. So while we look at this graph, it shows a nice smooth curve. There are actually fluctuations in that curve, and we need to accommodate those very quick fluctuation. We also want to have some resilience to failure. So if we have allocated a certain set of resources to meet this demand, if there is any type of failure in the system, we want to be able to accommodate that and still be able to handle all the requests that are coming into the system. So if we have, for example, two systems and they're handling 100% of our traffic and we want to maintain a 100% availability, then if one system drops off, the second one needs to be able to step in and handle that additional capacity. And finally, scaling in the cloud is somewhat reactive, and it does take time to scale. Scaling is not instantaneous, and so we always need to have a little bit of padding in there in terms of time to allow us to scale up, bring systems online, and start taking traffic. Another concept, and many of you may already be familiar with this when we think about scalability, is that we need to view our resources in the cloud a little bit differently than we may have in the past. You know, back in the day, we treated our servers like pets, and that's really this whole pets and cattle analogy. Is we treated them like pets. If one of our servers was experiencing problems, we would spend the time and the money to repair it and bring it back into operable condition. We'd nurse it back to health when it wasn't doing well, just like we would do a pet. We would take it to the vet, we'd make sure that it got all the medications and the treatment that it needed, and then we'd bring it back home. In the cloud and in a truly scalable environment where our resources can come and go depending on demand, or perhaps they even fail, we take a little bit of a different view of this, where we think of them, individual resources, as part of a herd, and with no one member being any more important than the other. And in this diagram, it kind of demonstrates, you know, if one member of our herd fails or is no longer performing, we simply replace it with another one, and in this case, we put that one out to pasture. And this makes sense. You know, if it's a web server fleet that we have running, and maybe we have hundreds of instances, we simply take a failing instance out of rotation and bring another one in its place. And I'll talk a little bit later about some of the implications of that, but in general, that's the approach that we have to take in a scalable environment. One of the other things to think about in a scalable environment is state. And oftentimes when we're talking with customers about building out super scalable environments, we ask questions about what kind of state is maintained on this system. If you have an application tier and you want to make it super scalable, we need to think about what state is maintained on that system. And that state can come in many different forms. It can come in the shape of a file on disk. It can be a database. It could be images or files or media files uploaded by users. All of those constitute state on our system. They are things that we would need to recover in the event a system failed. And a good example of this, a fairly common example of this, if you think about a web server tier, is session state. So imagine a case where a user logs into your system, they go through a load balancer, and they're directed to one of the instances behind that load balancer that's handling web traffic. Maybe you have tens or hundreds of these servers up and running. When that user logs in, they're directed to an available web server based on some load balancing policy, and their session info is potentially stored on that web server. And so then the end user makes subsequent requests into that web server, and they're redirected back to that same web server that has their session state, and they can go on and on like this, so long as they're going back to the same server. Now, in the case of a scalable environment, some of those servers may come and go depending on the demand on the system. And in this case, it's demonstrating what happens if the web server that user is currently going to disappears. Well, in this case, if we're maintaining state on the server, all of a sudden that session state disappears, and then the user ends up either having to log back in again or potentially losing any information that was stored in that state. And in some cases, it may simply be an inconvenience. In other cases, it may mean that the user loses some work or some data that they're working on. So anytime we're talking about super scalable architectures, we always want to know where state is maintained in the system and come up with alternatives for that. In this case, we may want to store session info in a distributed memcache caching store. We may want to put data files up in S3 or on a shared file system, and databases, of course, in RDS, but thinking about those things. I'll switch gears then and talk a little bit about associated cost, and talk a little bit about what some of the things are that we can do to address cost issues or cost implications of running in scale in the cloud. And so first, let's talk a little bit about right-sizing our system. Right-sizing is what we do when we're trying to match our capacity to our demand at a more granular level. And this really a lot of times comes up when we're talking about matching EC2 instances to a current application. And right-sizing is really about choosing the right instance. And a lot of it depends on the information that you currently have. It usually depends a lot on where you are in your development and product cycle, what information, where you're coming from, what information you have about your workload. So say, for example, you are moving an application to AWS and you're trying to optimize your choice of EC2 instances. If you're moving from an environment where you currently have this application running, whether it's in a dedicated or you're in a colo and you have servers running already, you have some idea of what the capacity requirements are for your applications. You're running on a 4-core server and you've got 32 gigs of RAM. That gives you a great starting place to decide on the EC2 instance that you're going to use, with the caveat that you probably over-allocated that dedicated instance to deal with some capacity issues later on down the road. But that gives you a good starting place to start with. But oftentimes we don't have that information, or we're just making a guess. And so the first thing we want to do is try to characterize our application and put it into the right bucket, if you will, on AWS. So what EC2 instance type does this map to? Is your application CPU heavy? Is it I/O constrained? Does it require a lot of memory? All of those things will help you decide on the type of EC2 instance that you want to start with. This gets us in the right ballpark to begin with. And as my simple example here shows, you don't want to choose a bus when really you need a small sports car. If you're a small family and you got one pet, you really don't need a bus to carry you around. At some point you may need that capacity, but you currently don't. So let's go ahead and pick an instance type and size that's appropriate for your workload. Now the nice thing about working in AWS and working with this infrastructure is we don't have to get it exactly right on day one. If we build out a scalable system that allows us to scale on demand elastically, then even if we're a little bit off on our selection of EC2 instance type, our system will scale up and down to meet that demand. Getting the instance type dialed in is usually not something that happens on day one. That over the course of time we'll continue to refine that and continue to dial that in. And so long as we build out a scalable system, we're okay. Sometimes it may feel like when we're choosing an EC2 instance that we're throwing a dart at a dartboard, but a lot of times that's okay. As long as we get it in the right section of the dartboard, we're okay. We can continue to refine in after that. The next topic around cost usually comes up when we start thinking about reserved instances. Now, if you're unfamiliar with reserved instances, this is a mechanism that AWS provides to AWS customers that allows you to essentially indicate that you're going to want to use this particular EC2 instance type for a period of time, or RDS instance. There are a couple of different cases here. That you're going to want to use it for a particular period of time, and in return for doing that, AWS gives you a significant discount on that EC2 instance, and depending on the term that you require, whether it's 1 year or 3 year, and the instance type, you can see from 30 to, I've seen up to 75% savings over the course of a reserved instance lifetime. Now, a typical use of reserved instances, and I'll talk about what's in the graph here, is you have a particular workload, and you see your demand over time has established a baseline, and that's seen here below the dotted line in this graph, that you see a baseline of demand that you want to reserve capacity for. You know that you're not going to go below that, and that's a good case for reserved instances. And so you purchase reserved instances that are sufficient for that particular demand. And above and beyond that, you continue using on-demand instances. So you have reserved instances that are there for you to meet that constant demand, and then you use on-demand on top of that, just like you normally would. Now, some people go even further than that. I think Netflix is a good example where they actually reserve all of these, and those peaks and valleys you see in the on-demand section here, they actually establish their own spot market internally within their company, and allow other groups to use that. One of the questions that we see very often about reserved instances is, should I purchase reserved instances on day one? I really want to realize that cost savings. And oftentimes the answer to that is probably not, that you should usually wait, and maybe that's a month, and just make sure that you're choosing the right instance type. There are some restrictions when you buy reserved instances. There associated with particular regions, and in some cases availability zones and families. And so once you choose one, you end up having to use that instance for the duration of that. Now, AWS has recently introduced some more options around flexibility that allow you to convert your reserved instances to other types over the course of time. It used to be much more difficult to do that, but now you can change your reserved instances with a little more flexibility. So in addition to reserved instances, there's another way to purchase capacity in AWS, and that is through the use of spot instances. So you have on-demand, which is capacity that you can purchase on an hourly basis. You have reserved instances, which allow you to essentially purchase capacity over a long term and achieve a significant savings over the course of that reservation. The third way you can buy EC2 instances and compute resources is through AWS's spot instances. And if you think back to sort of the typical demand, the cyclical demand graph where you have your weekly cycles or monthly or business cycles, and you have this very high capacity, say on Black Friday, or very high demand on Black Friday, and throughout the rest of the year you have lower demand, you have all of this excess capacity. What AWS does with that excess capacity is they sell it back to us, in this case, in the form of spot instances, and those are EC2 resources that currently aren't being used, and you can buy them essentially for pennies on the dollar. You bid for those resources with other AWS customers, and so if you say, for example, you need an M4 extra large instance and you want to bid for it on the spot market, you place a bid for that. If your bid is higher than other AWS customers, you'll get those resources. However, if another AWS customer comes in after the fact and outbids you, those resources could go away. So I want to talk about that just for a couple seconds. So in the example I'm showing on this slide, this is a pretty common one where you have a set of users who are using some particular resource and they're submitting requests to your system. And in the upper track, those requests are queued up, and you have a back-end system that scales based on the depth of that queue. So for say this was a premium customer who paid for your service, you might have a set of reserved instances that were handling the baseline demand on your system, and then have on-demand instances scaling up and down to handle additional requests. As queue depth grows, you would add more on-demand instances to handle those requests. And so you have this sort of normal scalable system based on queue depth. Now what happens if you wanted to offer maybe a free model for some of your customers, a freemium type of approach where you allowed them to use your system with low or no cost, but you wanted to save money on your end? You could implement a very similar model as shown in this diagram where you use spot instances to handle those requests. So from your free customer's perspective, the system might not be as responsive, or they may have to wait a little bit longer to get their request processed. But on the back end, you would save money by using these spot instances. Now, one thing to note about your use of spot instances, as I mentioned earlier, they can come and go fairly randomly. So if another AWS customer bids on those same resources and outbids you, those resources, those EC2 instances, can go away. And so you need to make sure that the work that those EC2 instances are doing, those spot instances are doing, is either idempotent or can be recovered or is resumable. So a good example of that would be maybe you had a service that was resizing images or watermarking images or something like that, making sure that you could restart that process if the EC2 instance that it was running on for whatever reason, was no longer available. In this case, it was a spot instance that was you were outbidded on. But I want to stop for just a second here. It looks like we have a couple of questions in the queue. I'll see if I can answer them. One of the questions is what is a good approach to securing your scalable AWS Cloud environment? I don't talk a lot about it in the slide deck, but security is one of the other attributes as a solutions architect that we look at when we're talking with customers, is what mechanisms are in place to secure this environment. And it depends a lot on the application and the customer itself. We'll utilize whatever AWS services and features are available using particular IAM roles, identity and access management, establishing users and roles to control access into this system, so that access into EC2 instances or the permissions that those EC2 instances actually have to access other AWS resources and services is utilized. You can also utilize data encryption both in flight and at rest, so you can establish secure connectivity between EC2 instances inside this environment and other services. You can use ELBs to terminate SSL connections at the front end of these environments. You can use encryption of EBS volumes on EC2 instances to secure those volumes. We actually have a security white paper that's been published. I will go ahead and provide that link to everybody so you can take a look at it and read it at your leisure after this. One other question is around applications that are designed not to scale, and I'll see if I can address this question. So oftentimes we do see applications that are, perhaps it's a commercial off-the-shelf application that you have running and you want to move it to the cloud, or it's some legacy application that is not cloudy and you want to move it to the cloud. Unfortunately, you can't, or you don't want to ever have more than one of those instances up and running at the same time. This could also be because of licensing reasons. You only have one single license. So you can't really make that scalable other than scaling it vertically. So you can scale vertically by moving from one EC2 instance size to another. For example, you start with a C4 large instance, and you decide you need additional capacity, so you move to a C4 extra large or C4 2 extra large, and up the ladder until you reach the top. That is how you would scale that particular instance or that particular application in this environment. Now, there are other questions around availability. I haven't really mentioned it, but one of the things that we also get when we implement a scalable environment usually is a highly available environment too. Because we're able to scale out horizontally, we now have some redundancy in our system. And in the case of a singleton application like the question was around, you really don't have that redundancy. And there are other mechanisms to put in place to ensure or to minimize downtime in case there's ever a problem with that instance. So I'll move on to the next section, and this one focuses a little bit on development. And I come from a development background, and so these are some of the things that I've learned over the course of time, and some best practices that we've established at Rackspace for working with developers who are developing applications for the cloud. So I want to start with one thing, and there are actually two components to this. There's logging at scale and also monitoring. And unfortunately, I don't have anything here on monitoring, but I'll try to bring it up as well. In a distributed environment, regardless of whether you're scaling or not, but in particular in a scalable, elastic environment that's distributed, logging is a critical and key component in this environment. It's one of the building blocks for building a maintainable, manageable, supportable, scalable application in the cloud. And the reason for that is really this. If you look on the right-hand side, and I hope this is large enough for everybody to see here, in this scalable environment, if we have tens or hundreds of servers running in an environment, say it's a web server, for example, that's a good way to explain this. If there's a problem with one of those web servers, and thinking back to our pets versus cattle analogy, if there's a problem with one of those servers, we don't bring it back to life. We don't try to nurse it. We don't triage it. We don't try to repair it. We simply take it out of rotation and bring another one up in its place. And when we take that instance out of rotation, in this case, it's it could be a system failure. It could actually be a scaling event. Once that system is taken out of rotation, it no longer exists. Any logs that were stored locally are no longer there. Any metrics that were stored locally are no longer there. They're gone. And so in a distributed environment, if we want to log, we need to move those logs off of those systems as quickly and as soon as possible. And so we start looking at logging infrastructures. And in order to do that, we want to make sure we have a logging infrastructure that is reliable, that it can survive in the event of networking issues, network partitions, slowdowns, that it's capable of accommodating spikes in traffic, that it's capable of very high throughput, and it's also capable of low latency operations. Now this starts to sound like a typical service in the cloud, and it really is. Logging becomes a tier 1 service in our application, and you start to see applications like in the lower left here where we build up services that have agents installed on them. And in this diagram, the little A in the box is an agent, and that agent is responsible for shipping logs off of that instance. So in the web server example I mentioned, HTTP logs, access logs, error logs, all of those should be shipped off of that instance and aggregated in some central repository. In this case, the agents on individual systems, they send those, they take those logs and they send them to a source aggregator, and that source aggregator then sends them to a back-end logging service, which may have a load balancer in front of it for load balancing across multiple instances. This particular design pattern has a scalable backend where target aggregators can then scale in and out based on demand, just like a normal application would, and then store them in a highly available, durable database. And so the actual logging architecture looks like any traditional application architecture in the cloud. And I wanted to mention that, along with logging, we also need to consider monitoring. And that really means the same thing, that once these systems go offline, once they're taken out of rotation, that information is no longer available. So we do things like instrumenting our code, aggregating our metrics, and shipping them off to a metrics aggregation service. And I'll mention here because they're fairly easy to use. That would be CloudWatch on AWS. In terms of logs, you could also send these off to your logs off to CloudWatch logs to aggregate them, and then be able to query them later on if there is a failure and you want to go back in and triage, do some forensic analysis of your logs. You can do that because once that instance is gone, it truly is gone. One other thing that I want to talk about at the developer level is around resiliency and fault tolerance in the cloud. And I don't call it out here, but Werner Vogels, who's the CTO of AWS, he has a very famous quote, at least within the AWS circle, is everything fails all the time. At some point, every component in your system is going to fail, and you need to plan for that. And I call it, you have a date with failure. It will happen in your system at some point, and you just don't know. You don't know when it's going to happen or where it's going to happen, what level it's going to happen in, the extent of it, or how long it's going to take. What you can do, though, in the face of that uncertainty is you can plan for it. And that's really the point here, is that we need to start thinking about our applications and our application stacks in terms of failures, and identify those single points of failure within our system, and understand and plan for what types of actions we're going to be able to take. We need to look at it from the top down, starting at really at the DNS layer. What happens if your site is unreachable? So say you have an external service that you're using to ping your site, and it responds with a failure, or your site is unreachable. What are you going to do? Do you have a failover strategy in place such that your users just don't see a blank screen, that your site is unreachable? How are you going to address that? Moving down the stack a little bit, what are you going to do if a web server fails? How are you going to handle that? And in a scalable environment like we've been talking about, that buys you some level of high availability, and so we use that to our benefit, such that if an EC2 instance fails in our scalable environment, we use auto-scaling groups to automatically bring another one back up in its place. What happens if an availability zone in AWS fails? What's your strategy going to be there? We always architect solutions that span multiple availability zones. What happens if our systems can't scale fast enough? What are we going to do in that case? Now, I bring this up because oftentimes these failure cases aren't strictly binary. It's not simply it works or it doesn't. We need to be thinking about that gray area in between and think about alternatives. Can we degrade our service instead of simply failing it and not operating it? Other questions as we move down the stack are, what do you do if your caching layer is unresponsive? How do you handle that? Instead of just falling over, do you simply go directly to the database in that case? So we want to make sure that our systems are designed and built and coded to not be so brittle that they don't have a recovery path in case some of these failures happen. Even in the case of a database failure, what do you do in the case your underlying database fails? Well, you may be able to degrade into read-only mode, for example. Just thinking about all of those, looking at all of those points in your system and identifying what the failure points are and what your action is going to be when that does happen, and making sure that that's codified in your application and that you have strategies or processes in place to deal with that when it happens. One of the things I like to call out too is occasionally there are outages on AWS, and usually we hear in the next day or two of different AWS customers who have had problems and whose customers couldn't reach them. What you don't hear about, though, are those customers who didn't have problems, who designed their systems to be fault tolerant and resilient and didn't have an issue with an outage of one particular time. And that's really where we want to get. We want to get to the point where we're not newsworthy in the event that there's any type of outage or service disruption on AWS. That from our customers' perspective, it's business as usual. The third thing I'd like to talk is just a little more detail around defensive development and how we can code defensively in our applications to handle some of those failure points. One of the things that we want to do is we want to plan for problems, and we want to plan for problems and have code in place to deal with those as if they do come up. And some of the common strategies, and I want to cover one design pattern here today, is the circuit breaker design pattern. And just to cover it real briefly, imagine you have a client and server application, and we can go back to the previous slide where we're talking about, say, for example, the caching layer. I have an application that utilizes our caching layer and to get data, and if that data is not present, then it goes to the server to obtain that data. What happens in the case that caching layer becomes unresponsive, as was the question in the previous slide? What if we start seeing timeouts at the caching layer, what do we do? Well, what happens a lot of times if there's no strategy in place is those timeouts start building up, and so you start seeing errors in your system, and you start looking at graphs, and you start seeing activity that's taking exactly 60 seconds, if that's the timeout value, to occur. Those timeouts start backing up, and that timeout starts bubbling its way back up to the top of the system, and you have this sort of cascading failure of your system. The circuit breaker is a design pattern that's intended to mitigate some of that effect. So it actually monitors that request from client to server, in this case from cache client to the actual cache itself, and if it starts seeing errors like timeouts occur, and it may use a simple metric like the number of times this occurs, it may shortcut that. It may trip the circuit breaker and say, okay, for the time being, we've seen enough of these, let's go ahead and redirect all requests directly to the database. Now that means potentially that latencies are a little bit higher for your customers while there's a problem, but they're not timing out. They're not seeing that 60-second timeout that they were seeing before. And then the circuit breaker, all requests continue to go through the circuit breaker and they're redirected to the server itself, but the circuit breaker occasionally tests that connectivity again in an exponential backoff type of form where it waits a couple of seconds, a couple more seconds, and then that continually grows. And when it detects that it's back to business as usual, it will start redirecting those customers back to the cache in this case, or whatever the server was. And so it's a case where it's not simply a failure or success, but let's do something that provides a good customer experience without completely failing it over. And the example I give it sort of in the lower left here is it's very common to see this in code where you have a try block, you catch everything, and you do nothing. You completely mask it or ignore the error. Instead, we want to do something like we want to try some operation. We want to catch something specific. In this case, it's a timeout condition when they're trying to reach the cache. And if we detect that, then let's go ahead and degrade that service, and if possible, such that the customer experience, while not perfect, while not optimal, is still a good customer experience, although somewhat degraded. So I'll go ahead and look real quick. I think I have time for maybe one question in here. Let's see. There's a question about spot instances from the last section about when could I use spot instances knowing it's a risk someone may outbid my resource? And that really goes back to what types of jobs you're doing with those spot instances. I mean, generally, you can save a significant amount of cost by using spot instances, but you have to realize, as was mentioned, that those spot instances can disappear at any time. So you want to make sure that the jobs that those spot instances are performing are resumable. So you want to make sure that if you have a spot instance that is running for 45 minutes and doing a particular job, if it stops at minute 46, that you don't necessarily lose all 45 minutes worth of work that you've done. So you want to make sure that those jobs that those spot instances are working on you can resume them, or you can very easily redo those jobs to make sure that they're immutable. Other questions, let's see, cost estimation tool around the use of RIs, etc. There are a lot of estimation tools that allow you, either third-party tools. Our Rackspace Compass tool also provides guidance around when to look at the use of RIs. So if it notices that you have a constant demand on systems, then it will make recommendations on RIs. Typically, as I mentioned, it ends up being you have a steady state capacity requirement in your system that you don't expect to decrease over time, that it will be there and not go away. All right. Well, a couple more questions. We'll try to get back to those as we near the end. The last section I wanted to talk about here is around operations and operations in a scalable environment. And this kind of goes back to sort of the whole DevOps model, although it's not just a DevOps thing, and that is automating all the things. The DevOps model, I mean, just in general, when we get to the point where we have a truly scalable environment, we want to automate as much of that environment as possible. We want to automate the introduction of new instances into the environment. We want to automate deployment of code to these environments. We want to automate development, the development processes in these scalable environments. If you think of sort of in a smaller environment, or perhaps in a development environment, you know, it might be very common for individual developers to, say, for example, SSH into an individual instance, update the code on it, and put that instance back into rotation. When you get to the point where you're operating at scale and you've got tens or hundreds of instances running at the same time, that's no longer an option. That really isn't feasible. So you have to have some mechanism in place, for example, to automatically deploy code, and you have to have some form of continuous integration and continuous deployment mechanism or tool set in place to automate that. As is true, you know, with the DevOps evolution, or the evolution of DevOps, we want to evolve our practices. We want to evolve the mechanisms that we use. We want to evolve the tooling that we use to work in this environment, to make sure that we're taking advantage of all of the services and features that are out there. And lucky for us, AWS provides a lot of those mechanisms for us. They provide tools like code pipeline, code deploy, code commit that allow us to automate this process so that we can truly move towards this, you know, break down all these silos between the different groups and organizations that we're parts of, and move to this environment where we are continuously improving our product, continuously improving our process. We're no longer synchronously handing artifacts, build artifacts over to new teams, or test environments over to other organizations, that we move to an environment where we're all working together as one team and continuously improving. One of the questions that comes up quite often is, and I mentioned earlier, is deployment model. So in this environment where we potentially have maybe hundreds of instances running at the same time, maybe tens of application layers, we've got web servers, maybe we have organized our architecture in a microservices fashion where we have tens or hundreds of individual services. How do we automate deployment to those environments? How do we manage that at scale? And like I mentioned on the previous slide, we automate everything. We want to automate all the things. And we really want to do it in such a way that we are able to produce a repeatable, predictable behavior in our system. And as part of that process, we want to try to minimize interruptions and downtime. And there are several ways of doing this, and I don't call them out here on the slides, but there are several mechanisms in AWS that we can use to deploy code. Code deploy is one obvious choice just because of its name. It allows you to automate deployment of your code. You can do a rolling deploy out to your environment and update code in that way. You can use other tools if you're using tools like Capistrano, or there's tools like Webastrano or Octopus on Windows. All of those provide automation capabilities and integration into AWS. One deployment model that is fairly popular and we see quite often, and many of you may be familiar with it already, is a blue-green deployment model. And that really is the diagram in the upper right demonstrates. as opposed to doing a rolling deploy where you are sequentially updating individual EC2 instances, for example, with the latest code, you actually stand up a separate stack and make a switch over to that new stack, and that it's termed blue and green. Blue bring stack, which you then switch over to. And there are a couple of different places talking specifically about AWS where you could do that switch over. One is at DNS, you could build a new stack and simply update it to point to the new ELB. You could use DNS to do that. You could swap out the ELB. You could swap out individual EC2 instances, or you can do the switch at the auto-scaling group. And in this case, best practice is usually around the auto-scaling group, simply because there could be DNS TTL issues. And I can answer questions about that later. But this is a very, very common approach and used in a lot of environments, big and small, microservice environments, containerized environments as well, one that we commonly see and recommend for customers on a fairly frequent basis. One other question that we very frequently get is around the use or how to build AMIs, and it's probably one of my favorite questions to answer and to talk about. And I won't go into a whole lot of detail. There's a lot of detail on this slide, but AMIs are the machine images that you use to run an EC2 instance. So it's an image that contains, at the very basic, the operating system, and a lot of the machine images provided by Amazon are just that. It's a base operating system. It's Ubuntu, or it's Amazon Linux, or it's Windows. And then you build on top of that. You can install your application dependencies, your application itself, and the configuration associated with that application. And there are different ways of deploying or using that AMI in AWS. In a scalable environment, you can use, as demonstrated sort of in the lower right-hand corner here, a basic AMI, which consists mainly of just those foundational components, and then at runtime you bootstrap your instance. When the web instance comes online, it has the operating system. It goes out and downloads the latest dependencies, gets the latest source code from GitHub, and then gets the configuration. Once it has all of that, it is then able to start taking on web traffic. And so that's the very basic model. It's super flexible because all of this is generally scripted, and so you can change that scripting very easily. As you can imagine, though, if this were in an auto-scaling environment and you wanted to bring this instance up very quickly, it could possibly be slow because it has to download all of that and configure the instance. On the other end of the spectrum, you have a baked AMI, which is essentially a golden image that you have everything already pre-baked onto it. So you have the operating system, your dependencies, all of your applications, and configurations, such that when a new EC2 instance is started up in your auto-scaling group, it is immediately able to start taking traffic. So this is the fastest route to take. It's the least flexible, though, because anytime you have changes to your environment, you have to bake a new AMI. In the other case, the basic case, you don't necessarily have to create a new environment. You just update scripts. More often than not, what we see from customers is sort of a hybrid approach here, where you create an AMI that you're going to use. You bake in all of those things that change infrequently, such as, of course, the operating system, any applications or frameworks that your application uses that don't change very often, and use that. And so in an auto-scaling group, when this instance is brought up using this AMI, all it has to do is go out and get your latest source code and configuration, and it's ready to run. So it's a good compromise between the basic and the baked EC2 instance, and provides you the ability to, number one, get something up fast, and gives you some flexibility then in what you put on it. The fourth item I wanted to talk about under operations is just tools, and so tooling. And I apologize, this slide is probably an eye chart for everybody. But really the point here is there are a lot of tools out there that you can use to help automate your environment. Everything from continuous integration tools, continuous deployment, code repositories, all of these falling into sort of the infrastructure as code, trying to build this out so that we can build these automated environments that allow us and allow our developers to develop code, to have that code automatically deployed, to have it tested and integrated, and then moved out to our staging and production and test environments in as automated fashion as possible. So again, a big eye chart on here. There are lots of tools out there. I encourage anybody who's going down this path to start looking at these tools and start thinking about how you're going to use these tools in your environment from day one. So that's really it for me. I want to do a quick wrap up. We talked a little bit about some ideas, some key concepts around scalability, some best practices around costs, the things that you can do to optimize costs in your environment. Also talked about some development best practices and things we do as developers to ensure that the applications we're writing are able to take advantage of the scalable services and features that are on AWS, and then some operational best practices that we can use. I want to thank everybody for joining today. It was a pleasure being here. I'll look, and I think we have time to go over a couple of questions, and if you have any other questions, please go ahead and post them now. Otherwise, the video will be available after the conclusion of this webinar. So I want to thank everybody. Let's see. One of the questions that came up, looks like, was the use of how do you manage cron jobs and scheduled jobs without having to create simple workflow apps or run them on auto-scaled servers. That's a great question, and there are a lot of options here. Of course, yeah, you can do cron jobs, you can do scheduled jobs. One of the things that a lot of customers I'm seeing start to use now are scheduled Lambda jobs. And so moving towards, and I didn't talk about this at all during this presentation, but moving towards serverless architectures is a great way, number one, to achieve very high levels of scalability and to accomplish cron type activities. You can actually set up Lambda jobs on a schedule now. You can do every 5 minutes, every hour. They just introduced the ability to go down to every minute now. So depending on the type of job you're going to do, you could actually use Lambda to do that now. Let's see, other questions. I just saw one come up. Can you change an instance size without reboot? That one, no, you actually, so to scale vertically requires that instance be restarted. And so you'd have to bring that instance down, change the instance size, and then bring it back up. Now, typically the way we solve that from an availability perspective on AWS is instead of having just one instance running, we have multiples of them running, and you do that in sort of a rolling fashion. So you'd take one instance down, you'd update it while you still had other ones, the old instance types handling requests, and then bring new ones up in a rolling fashion. Let's see. Compliance standards you can meet on AWS. I can start to answer this. You can definitely do AC. We have a lot of customers who are running HIPAA workloads on AWS. There's a couple of interesting white papers that we can post on compliance on AWS, in particular HIPAA compliance, what services and features are covered by the AWS BAA and the Rackspace BAA as a Rackspace customer running on AWS. And the same is true with PCI. The same, you can run PCI workloads on AWS, again, making sure that you're doing things in a PCI compliant fashion, you can do the same. You can accomplish the same things in the cloud as you would on a dedicated piece of hardware. You can secure data in transit. You can secure data at rest. All of those things. And if you search for security on AWS, you'll find a list of all the accreditations and certifications that AWS has around these particular types of workloads. Let's see. Can we add, the question is, can we add a private Git repo in code deploy? So with code deploy, you can point it to a Git repo. That's actually a good question. I'm not sure off the top of my head if there's a distinction between a public repository and a private repository for code deploy. That's something that I can do a quick search on. One other question that just came up, what applications can we use CloudFormation for? So most of the applications out there, I think there are a few that don't have CloudFormation support, and some of those are obvious when you think about them. For the most part, all of the core AWS services are supported by CloudFormation. So if definitely EC2 and RDS and S3, all of those have support for CloudFormation. CloudFormation is usually kept pretty up to date as services are launched. They provide some level of CloudFormation support out of the box, and CloudFormation is the tool of choice that we use at Rackspace when we're building out customer environments. We templatize it all using CloudFormation and utilize CloudFormation to the extent possible to build all of these environments out. And so there are very few that don't have CloudFormation support. In that case, we have to do sort of a one-off.
Just very quickly to interject there, I just wanted to confirm you can actually use both public and private GitHub repos with code deploy.
All right, thanks, James. Appreciate it.
No problems.
One other question I see, a question around network bottlenecks on EC2 and what you should do there. And one of the comments was the use of EBS optimization or scale up, what you should do. I mean, in general, if you're seeing networking bottlenecks on EC2, then you want to look at the EC2 instance, the size that you're using. Are you using a large or an extra large, or one of the larger, an 8XL? Because they all have different network operating envelopes, and you'll see things like low network or medium or high, and that would be one of the first things that you want to do, is start looking at where that bottleneck is. Is it on the server? Is it downstream? Is it upstream? And then can you solve that by simply scaling your EC2 instance type vertically? That's usually the first step in addressing network I/O issues on those instance types. You can, if you have an EBS I/O issue, then certainly using EBS optimized instances is a good choice to make sure you have some of that dedicated bandwidth to that EBS volume. I think, let's see, if that's, I think that may be the end of questions.
One more about assigning multiple public IP to single instances that just popped in as well, right at the end. And so just to clarify that, you can actually assign multiple public IP addresses to single instances using a number of different methods. EIPs or ENIs or elastic network interfaces allow you to achieve that. I believe that was the last of the questions though, Jerry, unless you have a few more lined up.
No, I think that's it. So I appreciate, again, everybody coming today. I hope you got something out of this, and I believe the slides and the video will be made available offline Thank you very much.